Yeah, come in, please. We want to start. So this is the very first session of Popple about probabilistic programs and also a little bit about separation logic. Um, I am reminding you again that you can ask questions on Slido. The hashtag is Popple2019. And yeah, you can of course also ask questions in person. You don't have to wait until the end of the talk to post your questions, so you can, post them whenever they arise. Yeah, let's start. So we have 4 talks. Let's start with the first one. So the title is Formal Verification of Higher Order Probabilistic Programs. The authors are Tetsuya Sato, Alejandro Aguirre, Jill Bart, Marco Gabordi, Deepak Garg, Justin Hsu, and Tetsuya will give the talk.
Okay, thank you. Good morning. Thank you so much. And I'm very happy to be here today. I'd like to talk about our contribution to formal verification of higher order probabilistic programs. Now, I'd like to begin with our motivation. There are many applications of machine learning algorithms. For instance, image recognition, stock price prediction, and machine translation, and autonomous driving. Importantly, programs in these applications are naturally probabilistic. So, we have a natural question. What does it mean for these applications to be correct? In other words, what's the property of the probabilistic programs for these applications? We will see an example of a property of the probabilistic program. Here is the convergence property of the Monte Carlo method. Monte Carlo method is an algorithm that approximates the expected value. The algorithm performs in the following way. First, we sample a value x1, x2, blah, 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 xn from a given sample D. Then, we take an average of h of x1, h of x2, blah, 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 h of xn for given function h. Now, the average z forms a random variable. Also, by increasing the sample size n, the average converges to the true expected value. The below is an convergence property of the Monte Carlo method proved from the weak law of large number. For any small epsilon, the probability of error over the epsilon is bounded by some term. Now, we can write a probabilistic program of the Monte Carlo method. We will explain the program itself later. And importantly, the convergence property of the Monte Carlo method can be understood as a property of the probabilistic program. Also, the property contains many parameters, for instance, sample size n, and the small epsilon, and the variance of the random variable h of x. Also, we can discuss the relational property of the Monte Carlo method. Consider 2 runs of Monte Carlo method, differing only on functions. The left run of the Monte Carlo method approximates the expected value of h, and the right run approximates the expected value of k. Now, if true expected value is far, then we can separate the 2 runs of Monte Carlo method by increasing the sample size n. We saw a convergence property of the Monte Carlo method and such separation property of the 2 runs of Monte Carlo method. And then we obtain general motivation. How can we guarantee properties of a probabilistic program formally? Now, our contribution is we introduced a program logic-based system, PPV, for reasoning about unary and relational properties of a probabilistic program with continuous distribution. Let's see what are probabilistic programming languages. Intuitively, they are programming languages describing probability distributions. Also, they have special operators for distributions, random sampling, and conditioning. Also, it is convenient to support the notion of higher order functions. Let's see these components in the probabilistic programming languages. First, random sampling. The sampling operation samples a value from a probability distribution. In this picture, we sample a value x from a distribution over the real line. And then the operation of sampling is useful to make probability distribution. Let's think another sampling. We take another sample y from another distribution, and we assume the sampling of x and y are independent. Then we compose the x and y into the pair. Now, the pair follows from the product distribution of the previous two distributions. Now, we can write this procedure as a probabilistic program. Mnet is an operation of sampling and is also monadic bind of the probability type. The first line of the program corresponds to the sampling of x from a distribution. And the second line is the sampling of y. And then we compose x and y into a pair, and then we return. Overall, that program itself corresponds to the product distribution. We will see another example of sampling. We record the Monte Carlo method. Intuitively, Monte Carlo method is an iteration of sampling. In each, rhetoric is an operation of iteration, and in each step of iteration, this algorithm updates the average by using new sample x from D. As we have seen, we have a convergence property of the Monte Carlo method, and it can be seen as a property of this probabilistic program. Next, we move to the operation of conditioning. Conditioning operations filter the probability distribution with condition. In this picture, we consider a distribution over the real line, and we consider the condition of positivity. Then, the conditional distribution lies only on positive real. By using Bayesian theorem, the conditional distribution is given by using a likelihood function corresponding to the condition. We can write this procedure as a probabilistic program in this form. The query is an operation of conditioning, and the query takes a distribution and the likelihood function corresponding to the condition. We will see another example of conditioning. Consider the uniform distribution over the unit square and the condition that the x coordinate or the y coordinate is less than 1 over 2. And then we obtain the conditional distribution. Here, the small right upper square is filtered out by the condition. We can write a probabilistic program corresponding to the conditional distribution. Importantly, the uniform distribution over the unit square can be written as product distribution, which can be written as probabilistic program of sampling. It is convenient to introduce higher order functions in the probabilistic programming languages. Intuitively, they parametrize functions. Here is two examples of usage of higher order functions. In the left example, we parameterize the function h in the Monte Carlo method. And in the right example, we parameterize the likelihood function in the conditioning. Then we saw what the probabilistic programs and their properties. And we repeat our motivation. We want a tool for reasoning about probabilistic programs for various properties. Moreover, checking the correctness of properties. Program logics are tools for reasoning about programs. There are many kinds of program logic verifying imperative algorithms with continuous probability, and higher order discrete probabilistic programs. and specific properties of randomized algorithms. In this work, we wanted to integrate these kind of program logics, and we want a general program logic for reasoning about probabilistic programs. In this work, we give a logic-based framework, PPV, for reasoning about probabilistic programs for various properties. And by using the proof rules in the PPV, from these data, we can give a proof. So we will see overall pictures of the framework PPV. The system PPV consists of three logics. The first is the assertion logic PL, consisting of assertions and usual predicate logic over the assertions and axioms. And second is the unary program logic UPL, consisting of unary judgment and unary proof rules. And the third is the relational logic RPL, corresponding relational judgment and relational proof rules, which are used for verifying the relational property of the programs. We will see components in the framework PPV. The programming language of PPV is a higher order functional programming language with product, list, if else, and recursion, and so on. And we introduced the monadic type M for distribution. And we also introduced the monadic unit and monadic bind. Importantly, monadic bind supports the notion of sampling. And mlet can be written as a syntactic sugar of bind. For conditioning, we introduced the operation of query, which takes the prior distribution and the likelihood function. So assertions in PPV are predicates for statistical properties. To capture the statistical properties of a program, we introduce enriched expressions. We introduce the enriched expressions of expected value and rescaling and normalization. The below is an example of assertion. This assertion says that the real function f and the distribution mu over the real line satisfy the inequality that the expected value of f with respect to mu is less than 1, less than equal to 1. Axioms in PPV are basic equalities on enriched expressions. Here is the selections of axioms. The first and the second are the linearity of the expected value. And the third is the idempotency of normalizing operation. So, of course, there are many kinds of axioms. But importantly, once we prove the soundness of axioms, we don't need to see the detail of integration and so on anymore. Now, we introduce unary judgment. Unary judgments describe programs with property. And a unary judgment consists of the four components: typing, context, and an assertion called precondition, and an assertion called postcondition, and the program itself. Importantly, in the postcondition, we use a special variable R to capture the output of the program. Here is an example of unary judgment. Okay, we will see later. Okay, consider the conditional distribution, which we have seen, and we can write a unary judgment correspond to this. And the program part corresponds to the conditional distribution. And the postcondition is a simple property of this conditional distribution. Importantly, in the postcondition, we use a special variable R to capture the output of the probabilistic program, which is equal to the conditional distribution. Now, we also introduce relational judgment in PPV. They describe programs with relational property. And instead of one program, we consider a pair of programs. And also, we consider a postcondition containing two special variables for the output of two programs. the special variable R1 captures the output of the left program E1. And the variable E2 captures the output of E2. Okay, let's see the example of relational judgment. Here is the two runs of Monte Carlo method. Here, typing context, precondition which we will introduce, and a pair of program and post condition. And we consider two runs of Monte Carlo method differing only on functions h and k. And then we can describe the separation property of two runs of Monte Carlo method using the relational judgment. Importantly, in the post condition, we use a special variable R1 and R2, and using them, and we substitute R1 and R2 to the output of the two runs of Monte Carlo method. We saw unary and relational judgment in PPV. But we want a correct judgment. We want to have a correct judgment. To do this, we introduce proof rules in PPV, which derive correct judgment following the structure of programs. Here is the unary proof rules on the conditioning in PPV. This proof rules takes the two correct judgment of pure distribution and likelihood function. And then this rule derives the correct judgment of posterior distribution. Of course, we have many kinds of proof rules. For instance, the relational proof rules on the monadic bind. We saw components in PPV. We will see technical background of PPV. Roughly speaking, the PPV is based on the syntax of unary and relational higher order logic, reasoning about the deterministic higher order program given by Aguirre and his collaborator, and semantics of probabilistic programming language in the category of quasi-Borel spaces given by Helne and Spivor and their collaborators. And roughly speaking, our system is a combination of these two kinds of previous research. To combine them, we introduce new structures for distributions in the syntactic part. And we introduce the category of predicates over the quasi-Borel spaces to interpret the property of probabilistic programs. We record three logics in PPV. We interpret the assertions and judgment using the category of predicates over the quasi-Borel spaces. And then, so it is easy to prove the soundness of the logic PL. And we have three logic, and we can connect equi-derivabilities. And equi-derivability says that if we have a relational judgment, and it is derivable using the logic RPL, if and only if the corresponding judgment of assertion is derivable in the logic PL. For unary property, we have the same property. And using equi-derivabilities, we can prove the soundness of two program logics. Here is a take-home message. We give a logic-based framework PPV for reasoning about probabilistic programs and various properties. These data are given using unary and relational judgment. Thank you for your attention.
Yes, thank you very much. Questions?
Have you considered the existence of weakest preconditions or strongest postconditions?
Sorry.
Have you thought about weakest preconditions or strongest postconditions for the assertion logic?
So the question was about weakest preconditions and postconditions in the assertion logic.
Wait. Let me. we didn't consider explicitly the weakest precondition of the programs, and but in the category of predicates over quasi-Borel spaces, we can give a weakest precondition using the inverse image, because the category of predicates over quasi-Borel spaces supports any subset on a quasi-Borel spaces.
And what about strongest postconditions?
Probably it will be a direct image, but I didn't touch.
This is ours. So a question from the Slido. Are there canonical reasons for choosing the axioms that you picked?
Sorry.
Are there canonical reasons for choosing the axioms that you choose?
No, we choose the axioms following that what we want to prove.
So did you, another question from the slide, or did you think about proof automation?
Sorry?
Proof automation?
So right now, okay, sorry.
Keep answering the question.
Okay.